Yep.
What time on Friday will you have your...
I got to see when rooms are available, but I'll let you guys know shortly. Yep. All right, so over the weekend I gave you guys a problem of the day to work on with chair conformations. And I wanted you to do a chair flip, so draw the other chair conformation, and then draw the 2D line formula. So what I've done is I've drawn the chair structure for each of these. So I've just redrawn them and the top. And what we're going to do is we're going to try to represent this chair flip. So again, remember you can number your carbons. So I'm going to go 1, 2, 3, 4, 5, 6. And down here we have our footrest, right? Up here we've got our headrest. And so I'm going to take this footrest, I'm going to raise it up. I'm going to take this headrest, fold it down. And we've got a hinge between carbon 4 and 6. And a hinge between carbon 1 and 3, right? So now if we look at it, our new headrest is where our footrest used to be. This is carbon 2. And then we can go around and we can label this 3, 4, 5, 6. Whoop, and this should be 1. We still have this hinge between 1 and 3. And we have this hinge between 4 and 6. Okay, so we've drawn our chair flip. We have things numbered. If we look at carbon 1, should the fluorine be equatorial or axial? Equatorial. So we'll go in and we'll draw in this fluorine as equatorial, which means the hydrogen must be axial. And then if we go over to carbon 3, should the iodine be equatorial or axial? Axial. It was equatorial. So what I saw a lot of people doing was they said, oh, it should be equatorial. I'm going to draw it like that. Is that okay? No. If you look at that carbon, this carbon's pointed down. So if we look at it, the arrowhead's pointed down. That means the axial group needs to also be pointed down. So let's redraw this. And I'm going to draw this kind of hidden behind there. So we've got iodine sticking down. And we've got the hydrogen sticking back. Okay, let's do the same thing with the other one. Yep.
Is it wrong if you put carbon 2 where carbon 5 is? Or sorry, carbon 1?
As long as we're keeping the relative order correct, you can number it however you want. In this case, I numbered it the same order we would if we were naming it. Yeah. All right, with this one, we could note this 1, 2, 3, 4, 5, 6. Yep.
Is that one drawn wrong already? Or can it be?
Yeah, it's already flipped.
Yeah, the first one's already
Which one?
the one you're working on now.
One I'm working on next.
You copied it down.
Oh, it's okay. We'll still show the chair flip. Yeah, you can represent it either way. In this case, it doesn't matter a whole lot. It'll be fine. All right. I'll fix it on the key. We still have a hinge between these carbons. We can pull this footrest up, this headrest down. Now this is 1, 2, 3, 4, 5, 6. Now if we look at carbon 1, should that terbutyl group be equatorial or axial? Equatorial. So I'll label this one out here, TBU. We've got our hydrogen axial. And then carbon 2, should that methyl group be axial or equatorial? Yeah, axial. So we'll label this as CH3, and then I'll label this H sticking out there. So we just need to make sure that whatever was axial becomes equatorial, and whatever was equatorial becomes axial, right? All right, let's do the 2D structure. So let's imagine with the molecule on the left that we're looking down from the top face. Is the iodine going to be a dash or a wedge? It's going to be a dash, right? The hydrogen's closer to our eyeball, so that's going to be the wedge. The iodine is going to be our dash. So if we go down and we number this, we can say, all right, 1, 2, 3, 4, 5, 6. On carbon 3, we said that iodine is further away from our eye, so it's going to be dash. The hydrogen's closer, so it's going to be a wedge. Then if we look at carbon 1, is fluorine closer to our eye or further away? closer. So will it be a dash or a wedge? Wedge. So at carbon 1, we can fill this in, and we can say fluorine and hydrogen. And I had people asking me too, well, what about the 2D structure for the other chair? It's the exact same. A 2D structure doesn't account for axial versus equatorial. It's just a 2D representation of the molecule. All right, if we do the same thing with the next one, we can number our carbons. We can go 1, 2, 3, 4, 5, 6. If we look at carbon 1 and we're looking straight down on it, is the tert-butyl going to be a dash or a wedge? Wedge. Oop. So we can fill that in as a wedge. Say TBU. And then what about the methyl group? Is that going to be a dash or a wedge? Wedge. And it's coming off of carbon 2. So we can label this as CH3. And there we go. Easy enough? All right, let's, for the sake of argument, try to name these. Is the first one, the one with fluorine and iodine, going to be cis or trans? Trans. So in this case, we've got a trans compound over here. And the way we can tell is look at the hydrogens. They're on opposite faces of the ring, right? One's sticking back, one's coming towards us. If they're on opposite faces, they're going to be trans. If we look at the next one, is it going to be cis or trans? Cis. Cis. Perfect. So we can go through and we can name these and we can add the prefix cis or trans onto the molecule to describe the proper orientation of the substituents. This comes into play a lot because if we think about it, some people might have accidentally labeled it like that. Are those two molecules the same thing? No, they look really similar, but they're not. It gets kind of tricky. And so we do have to keep track of the absolute three-dimensional orientation of a lot of these molecules because it changes a lot about those molecules. And that's what Chapter 5 is going to get into. Yep.
How do you know which atoms to look at in relationship to cis and trans when we've got multiple different ones competing against each other?
Yeah, and that does get tricky. So with cis and trans, you're always comparing two identical groups. So in this first case, I'm looking at the two identical hydrogens. They're on opposite sides, so we call them trans. Over here, there's two assumed hydrogens, right? So let me draw in the assumed hydrogens. We've got one there, and we've got one there. These two are identical, and they're on the same side, so we call them cis. So cis and trans can only be used to describe the relative relationship of two identical substituents on a ring or a double bond. Yep. No, I didn't ask for that. We're just practicing for fun, you know. Okay. All right, let's get into Chapter 5 stuff. Chapter 5 talks about stereoisomerism, or more importantly, isomerism in general. What does isomerism mean? Yeah, I heard somebody say the same molecular formula, right? So isomers have the same molecular formula. So we can make a little flowchart here. We've got isomers up top, and we said that they're the same molecular formula. But not all isomers are the same. So we're going to break this down into some subclasses, and we're going to talk about these subclasses this week. The first subclass is referred to as constitutional isomers. So a constitutional isomer has the same molecular formula as another constitutional isomer, but a completely different connectivity, right? So do you guys remember talking about that when we were talking about intermolecular forces? These molecules are radically different from one another. They're not at all alike. We've taken those essential building blocks and we've reordered them in a completely different way. So constitutional isomers have a different connectivity. And this is one class of isomerism. The other class that we're going to talk a lot about are stereoisomers. So the way I like to describe stereoisomers is they're arranged differently in three-dimensional space, but the overall connectivity is exactly the same, right? So if you lift up your hands are the same but different, right? If I had my left hand chopped off in a horrendous accident and my doctor went and replaced it with a right hand, I'd be pretty irritated if I had two right hands, right? They're the same, but they're different. And they behave differently in the body as well. And we're going to look at a lot of examples where the handedness of a molecule changes the properties very dramatically. So stereoisomers have the same connectivity, but different 3D layout. So let's talk a little bit about stereoisomers, and specifically we're going to talk about the idea of stereocenters and chirality. Is there a question? What's that?
So our hand is a stereoisomer?
Yeah, if you think about our hands are the same, but they have the same connectivity, right? My pinky's still on my pinky part of my hand, same with my index finger and thumb. But three-dimensionally, they're laid out differently. They're non-superimposable.
Okay.
And so we're going to talk about that specific type of stereoisomer. Those are called enantiomers. And there's another type called diastereomers. So we're going to talk about both of those. The key point is that they have the exact same connectivity, meaning groups are coming off the same carbons, but they have a different three-dimensional layout. So for example, in one molecule, you may have a dash in one position, and in the other, you may have a wedge. They're both coming off the same carbon, but different 3D layout. Okay, so with stereoisomerism, we first have to identify stereocenters. Stereocenters can best be described as a position or an atom with 4 different substituents coming off. What I normally do, as soon as I find a stereocenter, I label it with a star. I really like to keep track of my stereocenters because they tell a lot about what's going on in a molecule. So let's take a look at a molecule, and I want you guys to help me identify a stereocenter. All right, the first molecule I have is one that's in most of your medicine cabinets at home. This is ibuprofen. Where is the stereocenter in ibuprofen? Which atom has 4 completely different substituents coming off of it? Check with the neighbor and see if you guys agree. I'm going to clean up the structure really quick. There we go. All right, raise your hand if you think you found a stereo center in ibuprofen. All right, a couple people. Raise your hand if you're still trying to figure this out. All right, a few more people. All right, for sake of argument, is that carbon down there a stereo center? No, why not? Yeah, it's got two methyl groups. That means we've got two identical substituents. That wouldn't qualify that carbon as a stereo center. So that doesn't work. What about the carbon next to it right there? It's got two hydrogens. That doesn't count. What about this carbon right here? It doesn't even have four substituents, right? That carbon's bonded to two other carbons and a hydrogen, so that doesn't qualify as a stereo center. All right. What about this carbon? No, it doesn't have four substituents. What about that carbon?
Yes.
Yeah, exactly. So if we look at this carbon, we've got a methyl group on one position. We've got an assumed hydrogen. We've got a carboxylic acid, and then we've got this benzene ring coming off. So this would qualify it as a stereo center. So the question is, when I draw ibuprofen, we could draw it two different ways. I could draw that methyl group as being a wedge, or I could draw that methyl group as being a dash. These are not the same molecule. In the same way that our left hand is not like our right hand, right? The interesting thing is when you buy ibuprofen from the store, it's a mixture of both of these. And so if you've got a mixture of both handedness types of a molecule, it's called racemic. And so in this case, it doesn't really matter which type we get. The body will actually scramble it up into a racemic mixture regardless, so we just sell it as a mixture. So let's take a look at another example. But before we do that, let's label this. Hold as a racemic mixture, meaning a 50-50 mix. Let's take a look at another example. And this was an example that somebody was talking about in my office today, so I thought I would put it on here. Let's identify the stereo center in here. You guys identify it? All right, so we've got a stereo center right here. So the question is, we have two different types of this molecule. Oops, sorry, this should be SH. We've got two different types of this molecule. We've got one where the NH2 could be a wedge. We've got another where it could be a dash, right? Is May here today? Are you back there? Oh, there you are. You're hiding. Do you recognize what this drug is? We were talking about it in our office hour, and you said that the pharmacist didn't know the difference between this and another. Yep. The top one, or this is penicillamine. The top one, where the nitrogen is shown with a wedge, is toxic. It'll kill you. You don't want to ingest this. The bottom one, where that nitrogen is shown with the dash, is used for a variety of different treatments, but primarily it's used for rheumatoid arthritis. So occasionally I have students say, Dr. Engel, why do we need to care about chirality? This is why. You don't want to accidentally give somebody the wrong type of drug because you could kill them. In the case of ibuprofen, the handedness didn't matter, but in this case, the handedness matters very, very much. If you give them the wrong handed molecule, it's going to kill them.
So the NH2 with the dash line would be
It would be what?
equatorial or
So we're not looking at cyclohexane, so we can't classify these as axial or equatorial. What we're going to do next is we're going to figure out how to name these because they do have different names based on their handedness. We do want to be able to distinguish between them.
So those are stereoisomers?
Yep, these are stereoisomers one another. They're different molecules entirely. In this case, one's bad and one's good. All right, I've got another example that I really like from history.
Hey, Dr. Engel?
Yep.
For the example you just had, how come it doesn't rotate between the two structures?
So if you think about it, it's locked as tetrahedral. You can't just switch out one bond and replace it with the other bond. So in the same way, I can't invert my right hand and form a left hand out of it, right? Without breaking some serious bones. It's the same thing with a molecule. We can't switch from one hand of a molecule to another hand without breaking a bond.
So you're saying like the thumb being a bone?
Yeah.
You can't switch that thumb on the outside?
Exactly. To make my right hand like my left hand, I'd have to pop off my thumb and put it on the other side. Same thing with molecule. You can't do that without making or breaking bonds. All right, the other example I like was a colossal failure by the pharmaceutical industry. Has anybody here ever lived in Germany? Okay, a couple people have lived in Germany. This was a really big deal in Germany, more so than the US. So we've got an NH here. Let me clean this up. And then we've got a CO double bond here. Let's identify the stereocenter. So let's quickly mention this one right here. Is that nitrogen chiral? Does it have 4 different substituents coming off? Well, we kind of could argue it does. It's got a lone pair. It's got a hydrogen. And then if we follow along this carbonyl, that carbonyl path is different than that carbonyl path. So they're treated as 2 different substituents. One caveat with identifying stereocenters is that nitrogens are never stereocenters. Nitrogens invert too freely. And so when we're looking at stereocenters, ignore nitrogen. Nitrogen never counts as a stereocenter.
Is that the only one that won't cover?
That's the only one that typically won't. If you go down to phosphorus, you can isolate chiral phosphorus compounds. That's down in the row because phosphorus won't invert as freely. So just remember when you're identifying stereocenters, ignore nitrogen. All right, knowing that, where's our stereocenter? Yeah, it's the carbon next to the nitrogen right there. All right, this drug is called thalidomide. Does anybody remember hearing about thalidomide? You remember what it did?
It had some pretty serious developmental issues.
Yep, they gave it to a bunch of pregnant women saying it'll alleviate pains associated with morning sickness and things like that. They ended up killing 2,000 people and causing permanent birth defects in over 10,000. It was on the market for 2 years before they realized it. The problem was one of the stereocenters in lab testing showed that it had good results, but our body scrambled it into both-handed molecules, and the other hand of it was actually quite toxic. So this was sold as a racemic mixture, or sold as a pure compound. But enzymes in our body made it racemic, meaning it was a 50-50 mixture of both-handed molecules. No, that's so when they sold it as one-handed version, but as soon as you ingested it in your body, your enzymes went to work and actually scrambled that stereocenter. So occasionally enzymes in your body will take a pure one-handed molecule and actually scramble it so that when it's done with the enzyme, it comes out as being both-handed.
What about
The penicillamine, your body won't scramble that one. We don't have an enzyme that will damage that stereocenter, so it remains intact. Yep.
So the red one, it attaches to an N
Mhm.
and then an O to a C.
Yep, so if we look at it,
So it's only 3.
And that's a hydrogen.
we've got this
Oh, okay.
hydrogen right there, right? So we've got the assumed hydrogen that counts as our fourth substituent.
Okay.
Yep, Fiona?
So the enzyme that made it racemic,
Uh.
is it only active in pregnant women or is it active?
It was active in all women. And unfortunately, the chemists at the company, there's speculation that they did know that this was a problem, but continued selling the drug regardless. So they were essentially active in killing over 2,000 people.
When was
Yeah,
the-
this is in the 1950s.
Oh.
Yep.
So was the nitrogen part, like where you said nitrogen is chirality stereocenter, was that just a pointer or did that have something to do directly with?
That's just a pointer because a lot of people will identify nitrogens as stereocenters and they aren't.
Okay,
Yeah.
so the only thing that happened as a result of this thing not working was that carbon stereocenter not being one-handed.
Yeah, exactly. That carbon stereocenter, as soon as it went into our body flipped it around into both-handed versions of this molecule, which was a lethal combination for a lot of women.
Could you draw the other?
Yeah, when you say both-handed, you mean like wedged in and...
Yeah, so let's...
I mean like the oxygen group somewhere else?
I can't remember which version of this molecule was sold, the R or the S. I can look that up. I feel like I'm a giant walking Microsoft ad. All right. So one version had a wedge here, right? And the other one, that ring was kind of pointed back into the page. So when it was digested, even though it was sold as one of these, the body converted it into both of these, which was toxic. Yeah, so it's a neat point in history, although a sad one. All right.
How come it's that one is the wedge of the dots and it's not like where the other one's connecting?
You could have picked any of the four positions coming off of it.
Oh, so
Yep.
that would be correct to do with any four?
Yep, any of the four positions you could have drawn as a dash or a wedge, and it would show it.
Okay.
Yeah, so now what we need to do is we need to learn how to name these molecules because obviously it's important which one we're referring to. Some of them could be considered quite toxic, others can be considered perfectly normal. So what I gave you guys was a handout with rules for assigning R versus S stereochemistry. And I'll kind of walk you guys through this. So the first thing you need to do is you need to identify your stereocenter and label it with a star. We just practiced that, so that's pretty straightforward. Next thing we need to do is we need to assign priorities to each substituent coming off of that stereocenter. And the way we assign priorities is we look at the atomic mass of the attached atoms. So our stereocenter is a carbon. If we look at the attached atoms, we've got one substituent where the attached atom's a nitrogen, another one where it's a hydrogen, another one where it's a carbon, and another one where it's a carbon. So which one's the heaviest atom? Nitrogen. We go to the periodic table, nitrogen's got the higher atomic number, so nitrogen's called priority number 1. If we're at a tie, so if we look at positions 2 and 3 as we're labeled here, we have to go into our tiebreaker rules. So we've got carbon versus carbon. The methyl one, that carbon has 3 hydrogens, where this one has 2 hydrogens and a carbon. So in this case, that breaks the tie. And this carbon, where the benzene ring is dangling off, gets priority number 2. This carbon gets priority number 3. And last but not least, hydrogen gets assigned priority number 4. Now what you do is you can connect 1 through 3. So you can see I had an arrow go directly from 1 through 2 all the way through 3. If your lowest priority is pointed backwards and your arrow is twisting counterclockwise or to the left, it would be called S. So does anybody know why it's called S and not L? Anybody know Latin? Yeah, the Latin word for left is sinister. So left is S. There's also another L conformation that we'll discuss later when we get into biochemistry and biomolecules. If it's rotating to the right, meaning clockwise, then we just label it as an R, which is Latin for rectus, which is right. So this is how we go about assigning the stereochemistry to a lot of molecules. It's important to remember that the R and S assumes that your lowest priority is pointing backwards. So if possible, try to orient your molecule so that the lowest priority is pointing behind you. If the lowest priority is pointing towards you, then the R and S designations kind of get flipped. So it's a lot easier if you just take that lowest priority and point it directly behind you as a dash position. So let's take a look at some practice problems. And I've got an example. We're going to assign R versus S to the following. And bear with me, this is a big molecule. There we go. This one's big. I'm going to make your hands sore. And then over here we've got a nitrogen with the methyl group. Does anybody have family members with cholesterol problems? This is one of the best-selling cholesterol drugs on the market. Crestor. Crestor, if you watch any TV, chances are you've watched a Crestor ad. It sells about $5 billion annually. It's one of the most prescribed drugs in the US. And it has not only one chiral center, but it has 2 chiral centers. Let's identify, or 2 stereocenters. Let's identify both of those stereocenters. No, it's good for you. It lowers your cholesterol. This one's not bad. It won't kill you. So we got to label them with stars. So raise your hand if you found 2 different ones. I know some people are still drawing it. Let me really emphasize this. All right. Yep.
Is that a carbon coming off of that sulfur?
Yes. This is a CH3. I'll label these as CH3s just so we don't get confused.
Well, no, I mean, it wasn't that it was confusing. It's just you double bonded that carbon, so I was.
They're both oxygens, sorry. That was my poor penmanship.
That's all right.
All right. Can you guys identify 2 different stereocenters? All right, let's label them. I see one stereocenter here. I'm going to label that in red. And I see another one over here that I'm going to label in blue. So can you guys identify both of those as having 4 different substituents? All right. We've got to assign R or S to both of these stereocenters. But let's just do one at a time and not get overwhelmed with this. So let's do the red one. It looks like we've got an oxygen right here. We've got a carbon here, and we've got a carbon here. Where's our 4th substituent? Hydrogen. It's pointed back, which is convenient for us. All right, what gets highest priority? Oxygen or carbon? Oxygen. Yep.
But don't you have two carbons there?
Yeah, they're two carbons, but they're not the exact same substituents. You see how the chain coming off to the left is different than the chain coming off to the right? So they're treated as two different substituents.
How about the OH one? Both carbons.
Yeah, if we go over to the blue one, same thing. If we look at the carbon chain going to the left, it's different than the carbon chain going off to the right. So the substituents treated as a whole. We're not looking at just the individual atom coming off, we're looking at the entire chain coming off. Okay, so oxygen gets labeled as position 1. All right, now we're in a tricky situation. We've got a carbon-carbon tie. All right, so what we do when we run into this situation is we could say, all right, this carbon is bonded to 2 hydrogens, right? So it's a CHH. And then we can look at this carbon, and so we could say this carbon is bonded to a CH, and then
Like the whole molecule, right?
so we've got a CHH. This one we have a CH. Exactly, I heard somebody say it. We've got a ghost carbon. So if we look at it, this carbon, which is over here, actually gets counted twice. Whereas with this carbon, over on the right-hand side, we're actually just counting this carbon. Or shoot, let me go back. Sorry, guys. All right. Bear with me. I'm going to start over. Rewind. All right.
Double bonds are all.
Oh, thank you. I'm backpedaling. This happens occasionally. All right. If we look at this carbon, what's coming off of it? Hydrogen, hydrogen, carbon. If we're looking at this one, what's coming off of it? We've got a carbon, hydrogen, and then the carbon gets counted twice because it's a double bond. So I guess I'm not really backtracking too much. I was just second guessing myself. All right, so which one would be assigned higher priority, the carbon on the left or the right? Left. So you do have to remember ghost carbons. So if you have a double bond, you have an extra carbon that's not figuratively attached, or not literally attached, but figuratively attached. And if you have a triple bond, you get 2 ghost carbons.
Does the rest of the giant molecule attached count at all? Or, I mean,
You go out until you break the tie. So if we needed to, we would continue going out to further and further atoms. But in this case, the tiebreaker was this double bond.
But can I just automatically assume, like, it's like a giant molecule attached on one side that's the winner?
Not necessarily.
Okay.
You have to go individual atoms out. So don't necessarily look at the size of the substituent. Okay, so now that we've identified our tiebreaker, no thanks to me, we can go through and we can do the arrow like that.
So we draw it going through the 2.
Yep, so 1 to 2 to 3. We connect that as a smooth curve. Our lowest priority is pointed backwards, which is great. Are we going to the right or to the left? Left. We're twisting to the left. Would that be R or S? S.
So if we were going like 1 to 5, that arrow would go from 1 through the 2, 3, 4 to the 5.
With stereocenters, we only have 4 substituents, and we're only connecting 1 through 3. So start at 1, go through 2, end at 3. 3 should be where your arrowhead's at, and you're going to be looking, is it going left or right? And try to have the lowest priority going backwards.
So the double bond is always stronger than the single bond.
There are some weird exceptions. I'll show you guys how to break ties, though, but you always want to go through and do that same thing we did where we said CHH and then CHC, and whichever one has the higher priority out of those groupings gets assigned the higher priority. So it had 2 carbons as opposed to the CHH, which had 1 carbon. Yeah. Yeah, you want to look at which one has the higher mass number. All right, let's do carbon 2, which is in blue. I want you guys to help me identify whether or not the blue one is R or S, and I want you to check with the neighbor. This one's a little tricky. Oops. Raise your hand if you think you've got it. All right, you guys are getting good at this. I like this. All right, what's highest priority? Oxygen. All right, then we go out to the next one. It looks like we've got a carbon versus carbon tie, so let's do the same thing. We've got a CHH. What about on the left-hand side? Same. So we go CHH. Oh, shoot, we're out of tie. What do? Go down the chain more. All right. So if we go down the chain one more carbon, we've got a carbon that's bonded to 3 O's. The double bond gets counted twice, right? And then if we go over here, we've got a carbon that's bonded to an oxygen, a carbon, and a hydrogen. So what's going to be higher priority? Yeah, what I do is I work down the list, so I could say, all right, OO, that's a tie. And then we go to carbon-oxygen. Oxygen's a higher priority, so this must be the higher substituent, right? Okay, so let's draw this in. So we would say 1, 2, 3. We connect this with an arrow. Would this be R or S? R. So a Crestor has 2 stereocenters in it, one that's R and one that's S. So we can go through and we can try to assign those appropriately.
What was the Latin word for R again?
So R is Latin for rectus, S is for sinister. All right. Do you guys know who the first person was that was describing the handedness of molecules?
Lewis.
Yeah, Louis Pasteur. He was the one who actually noticed that some crystals look differently under light. Does anybody remember what crystals they were?
Sugar.
Close. It was tartaric acid from wine. So he went to wine barrels, you get these crystals of tartaric acid. And he said that natural tartaric acid is RR. Tartaric acid, without using dashes and wedges, what's that? Oh, I have notes. This is tartaric acid. Where are our 2 stereocenters? It's where the alcohols are coming off, right? Let's determine whether or not those are dashes and wedges, and then redraw tartaric acid in its proper form. I'm just going to redraw our skeleton. So what do you guys think? The OH on the left stereo center, should that be in the dashed position
Yes.
or the wedge position? Let's try it. So oftentimes what I do if I'm stuck is I draw both, or I just try one and see if it's correct. If not, I flip it, right? So I heard dashed first. We'll do OH here. So what's highest priority for that stereo center? Oxygen. What's our next highest priority? Would it be the carbon on the left or the right? The left, because the carbon on the left has 3 oxygens coming off of it. The carbon on the right only has 1 oxygen. So the carbon on the left wins. So we go 1, 2, 3. All right. So it's going left, which is our S conformation, but why is this R?
Because the hydrogen's in front.
The hydrogen's in front. If the hydrogen's in front, we flip our rules, right? So ideally, we prefer to have it behind, but if it's in front, we just flip all of our R and S designation rules. It's pretty simple. So we can go through and we can label this R. Let's do the same thing for this one. Would the OH be in the front or the back? Let's try it. Let's try the front. So we've got OH, and I'll label H here. So what would be the highest priority? The oxygen. And then would the carbon on the right be higher priority or the carbon on the left? Right. So we would label this 2, and we'd label this 3, and then we could go through and say 1, 2, 3. Is that R or S? Lowest priority is pointing backwards.
S.
It'd be S because we're going left. Can you guys see how we're twisting left? It's going counterclockwise. So what do we need to do to fix this? Yeah, put the OH in the back. Now, the priorities remain the same. We go 1, 2, 3. If we connect these now, this would still be R. And then remember, that if lowest priority is pointing forwards, flip R and S. So they do need to be inverted if you've got the lowest priority pointing forward.
Can we explain on hand one when we came to the one that we did before? So the OH and the dash?
Because if the OH were pointing in the wedge position, we'd have an S position, not an R stereo center. All right, so for your problem of the day, you are being asked to identify stereo centers and then assign chirality to the last molecule. If you guys have any questions, feel free to let me know.